Imagine a force, unstoppable, relentless, tearing through the void. It crosses continents in the time it takes your eye to blink. Nothing in this universe can outrun it. Not rockets, not particles, not even the pull of gravity itself. For centuries, scientists believed this was simply how light behaved. An inherent property. But then, groundbreaking discoveries began to peel back the layers of reality, revealing something far more unsettling. The speed of light isn't just a limit for light, it's the ultimate speed limit of cause and effect itself. The maximum rate at which reality can update. Break this limit, and time, space, and logic simply blend into chaos. If you're ready, prepare to discover something that will shatter your understanding of the cosmos forever. Our story begins not in a gleaming laboratory, filled with complex instruments and equations, but on a quiet hillside outside Florence, back in the year 1638. Here, human curiosity pressed directly against the very edges of what our senses could perceive. Galileo Galilei stood there, a covered lantern in his hand, attempting something truly unprecedented, to measure the speed of light itself. He was already a legend, famous for daring to challenge established knowledge. He had watched moons circle Jupiter, proving not everything revolved around Earth. He had shown that motion followed rules far simpler, more universal than anyone suspected. Now, he chased a question that seemed almost philosophical: if light moved, just how fast did it travel? Galileo's idea was deceptively simple, beautifully logical. He and an assistant positioned themselves on distant hills, each holding a covered lantern. They rehearsed their timing with meticulous care. Galileo would uncover his lantern, sending a flash of light across the darkened valley. The instant his assistant saw that signal, he would uncover his own lantern in response. Galileo would then measure the delay between sending the signal and receiving its echo. Divide the known distance by the measured time, and the speed of light would finally reveal itself. On paper, the reasoning was impeccable. In practice, the universe flatly refused to cooperate. No matter how far apart the hills were, the returning flash appeared immediate. There was no detectable hesitation, no measurable interval between cause and effect. Galileo repeated the experiment many times, increasing the distance, refining his timing, recruiting assistants with faster reflexes. Each attempt produced the same result. The response seemed instantaneous, as if light crossed the landscape without spending any time at all. Galileo was too honest a scientist to force a conclusion where none could be supported. He recognized what his failure implied. Either light truly traveled infinitely fast, or it moved so rapidly that no human instrument, no matter how carefully designed, could hope to measure its passage across the small distances available on Earth. He suspected the second explanation was correct, but suspicion alone was not enough. His era simply lacked the scale required to expose the truth. What Galileo could not yet know was just how extreme the mismatch really was. Light does not merely move fast by everyday standards. At its true speed, it circles the entire planet more than 7 times in a single second. It crosses a 1-meter gap in a few billionths of a second. Human reaction time, measured in tenths of a second, is catastrophically slow by comparison. Galileo had been attempting to measure a fleeting whisper using a clock that ticked like thunder. To detect light's motion, science would need distances far larger than hills or valleys. It would need the sky itself. That opportunity arrived several decades later, not through clever engineering, but through the patient observation of a distant moon orbiting a giant planet. In the 1670s, a young Danish astronomer named Ole Romer was working at the Paris Observatory, assigned to carefully track the eclipses of Io, one of Jupiter's moons. Io followed a regular rhythm, slipping behind Jupiter, disappearing into shadow, and re-emerging on the other side with remarkable consistency. Astronomers treated these eclipses as a kind of cosmic clock, reliable enough to predict events years into the future. At first, Romer saw nothing unusual. But as months passed, and Earth continued its slow journey around the Sun, a subtle pattern began to emerge. The timing of Io's eclipses drifted, not randomly, but systematically. When Earth was moving closer to Jupiter in its orbit, the eclipses appeared earlier than predicted. When Earth was moving away, they appeared late. The discrepancy accumulated steadily, eventually reaching about 22 minutes across the full diameter of Earth's orbit. Most astronomers attributed this drift to imperfections in their models. Perhaps Io's orbit was slightly irregular. Perhaps Jupiter's immense gravity introduced subtle variations that calculations failed to capture. Roemer considered these possibilities carefully, and then, he rejected them. The pattern was too precise, too cleanly tied to Earth's changing distance from Jupiter. In 1676, Roemer proposed a daring explanation. The eclipses were not happening early or late at all. They were occurring exactly on schedule. What changed was the time it took for light itself to carry information about those events across space. When Earth was closer to Jupiter, light had less distance to travel and arrived sooner. When Earth was farther away, the same light took longer to reach us. The universe, Roemer realized, operated with built-in communication delays. Light was not instantaneous. By dividing the diameter of Earth's orbit by the accumulated delay, Roemer estimated the speed of light. His value was not perfectly accurate. It was off by roughly 25%. But the significance of the result overwhelmed the error. For the first time in human history, it was clear that information itself required time to move. This insight quietly transformed humanity's relationship with the cosmos. Looking into space now meant looking into the past. The sun we see is not the sun as it exists now, but as it was 8 minutes ago. Jupiter appears nearly an hour in the past. Distant stars and galaxies reveal ancient light, snapshots frozen millions, or even billions, of years ago. The universe we observe is not a single moment unfolding everywhere at once, but a layered archive of different times, stitched together by the finite speed of light. And yet, this discovery raised a deeper, more unsettling question: why this speed? Why should light move at this particular rate and not some other? What property of the universe fixed it so precisely? For the next 2 centuries, physicists pursued the answer with ever-increasing precision. Astronomers refined Roemer's celestial method. Engineers devised rotating mirrors and toothed wheels. Measurements grew more accurate. Error bars shrank. Decimal places multiplied. The value itself never changed. Light always arrived at the same speed. By the late 19th century, physicists believed they understood why. Light, they argued, was a wave, and waves, by their very nature, require a medium. Sound needs air. Water waves need oceans. Light, therefore, must ripple through something as well. They called this invisible substance the luminiferous ether. The ether was imagined as a strange cosmic material, filling all of space and permeating everything. Rigid enough to support waves traveling at extraordinary speeds, yet intangible enough to offer no resistance to planets moving through it. It could not be seen, touched, or measured directly, but it seemed logically unavoidable. If ether existed, Earth had to be moving through it. Our planet orbits the Sun at roughly 30 kilometers per second. That motion should generate an ether wind, just as moving through air generates resistance. Light traveling in the direction of Earth's motion should behave differently from light traveling sideways or against it. The effect would be small, but with the right instruments, it should be measurable. By the 1880s, physicists had instruments precise enough to detect it. The experiment designed to do so would become one of the most famous in scientific history. In 1887, Albert Michelson and Edward Morley constructed an exquisitely sensitive interferometer, an instrument capable of detecting changes in light speed far smaller than theory demanded. A beam of light was split into 2 perpendicular paths, sent outward, reflected back, and then recombined. If one beam experienced even the slightest delay due to Earth's motion through the ether, the resulting interference pattern would subtly shift. They mounted the apparatus on a massive stone slab, floating on Mercury, allowing it to rotate smoothly while isolating it from vibration. They measured at different times of day, different seasons, and different orientations relative to Earth's motion through space. They found no shift at all. No ether wind. No directional difference. No variation of any kind. Light moved at exactly the same speed in every direction. The ether, it seemed, simply did not exist. This result struck directly at the heart of classical physics. Waves without a medium made no sense. Even more troubling, every attempt to rescue the ether required increasingly contrived explanations. Some proposed that objects physically contracted in the direction of motion by just the right amount to hide the effect. Others suggested that time itself slowed for moving systems, again by precisely the amount required to preserve light speed. These explanations worked mathematically, but they felt profoundly unsatisfying. Nature appeared to be bending space and time with uncanny precision, simply to protect a single number. Why would the universe do that? By the dawn of the 20th century, physics stood at a crossroads. Either centuries of intuition about space and time were fundamentally wrong, or the universe was orchestrating an elaborate deception. Light's refusal to be measured like everything else was no longer a mere technical nuisance. It was a warning. Because once light refused to behave like an ordinary wave, it began to reveal something far stranger, that speed itself was not absolute, and that realization would soon tear space and time apart. Physics, at the close of the 19th century, had appeared complete, polished, almost finished, like a grand cathedral whose final stone had already been placed. Motion followed Newton's laws. Space was an invisible grid stretching endlessly in all directions. Time flowed at the same steady pace for everyone, everywhere, like a universal clock ticking in the background of existence. Light, scientists believed, was simply another wave, one that happened to move very fast through an unseen medium. Then, that single experiment quietly undermined all of it. In 1887, Albert Michelson and Edward Morley carried out what was expected to be a final confirmation of the ether's existence. Their interferometer was among the most precise scientific instruments ever constructed, capable of detecting differences in light speeds smaller than 1 part in 10,000. If Earth was moving through a stationary ether, the effect should have been unmistakable. It never appeared. No matter how the apparatus was rotated, no matter the time of day or the season of the year, light behaved as if Earth were perfectly still, or as if there were no ether to move through at all. The result was devastating, because if light did not require a medium, then it was unlike any wave physics had ever described. Worse still, the speed of light seemed stubbornly absolute. It didn't add to Earth's motion. It didn't subtract from it. It remained fixed, indifferent to the observer. This directly contradicted everything classical physics said about motion. In everyday experience, velocities combine naturally. Throw a ball forward from a moving train, and its speed adds to the train's motion. Walk into a headwind, and you feel the rain strike faster. There was no reason light should behave differently. And yet, experiment after experiment insisted that it did. Physicists found themselves trapped between two impossible options. Either the most precise experiments ever performed were wrong, or the most basic assumptions about space and time were incomplete. Many tried to save the old picture. Some proposed that objects physically contracted in the direction of motion through the ether, shortening themselves by exactly the right amount to hide the expected effect. Others suggested that time itself slowed for moving systems, again by precisely the amount needed to preserve the speed of light. These ideas were clever. They even worked mathematically. But they felt artificial, like scaffolding built to support a structure that no longer stood on its own. Why would nature conspire to distort space and time with such perfect coordination just to protect a single number? In 1905, a young patent clerk in Bern offered an answer that no one was expecting. Albert Einstein did not attempt to explain why light speed stayed constant. Instead, he simply accepted that it did, and asked what must be true about the universe if that were the case. His reasoning was disarmingly simple. The laws of physics, he proposed, are the same for all observers moving at constant speed. And the speed of light in empty space is the same for all of them, regardless of their motion. These statements sounded almost trivial when spoken aloud. Yet, taken together, they detonated centuries of intuition. Because if light speed never changes, then space and time cannot be fixed. Something had to give. What gave was time. Einstein showed that time does not flow at the same rate for everyone. A clock in motion genuinely ticks more slowly than a clock at rest. This is not a trick of perception or a failure of machinery. Time itself stretches. The faster you move, the more dramatic the effect becomes. At everyday speeds, time dilation is imperceptibly small. At speeds approaching that of light, it becomes overwhelming. Clocks slow. Processes stretch out. Aging itself decelerates. As an object approaches light speed, its internal time slows toward a halt. At the limit, time stops entirely. This single realization explains why chasing a beam of light never allows you to catch it. As you accelerate, your own time stretches. No matter how fast you go, light still pulls away at the same speed. Not because it accelerates, but because your experience of time has changed. Space does not escape unscathed. Einstein showed that lengths contract along the direction of motion. Objects in motion become shorter, compressed not by force, but by geometry itself. Space and time are not independent ingredients of reality. They are woven together into a single fabric, spacetime. Together, time dilation and length contraction perform a remarkable balancing act. They ensure that all observers, no matter how fast they move, always measure the same speed for light. Distances adjust, durations adjust. The ratio remains fixed. The speed of light is preserved not by coincidence, but by the structure of reality. This realization dissolved the ether completely. There was no invisible medium to detect, because light was not moving through space the way sound moves through air. Light was revealing how spacetime itself behaves. Einstein's equations carried another unavoidable consequence. No object with mass can ever reach the speed of light. As velocity increases, the energy required to accelerate further rises faster and faster. Near light speed, the energy demand grows without bound. To reach the limit would require infinite energy. Not a large amount. Not an impractical amount. But infinity itself. The barrier is absolute. Photons behave differently because they have no mass. They are not pushed up to light speed. They are born there. They exist only at that speed. For them, time does not pass in the way it does for massive objects. From emission to absorption, no duration elapses. This explains why nothing with mass can catch up. But it also raises a deeper question: why does spacetime have this structure at all? Einstein's theory explained how the limit works with stunning accuracy. It predicted every experiment with breathtaking precision. Atomic clocks flown on aircraft ticked differently than those left on the ground. Particle accelerators confirmed relativistic effects daily. Satellite navigation systems depended on these corrections to function at all. Relativity worked. Yet it felt incomplete. It described spacetime as smooth and continuous, like a perfectly polished surface. At the same time, another theory was emerging that described the universe as granular, probabilistic, and deeply strange: quantum mechanics. Quantum theory revealed that particles behaved like waves, that energy came in discrete packets, and that certainty itself had limits. The universe at small scales was not smooth. It jittered. It fluctuated. It existed in superpositions. Relativity and quantum mechanics were both correct, and they refused to merge. At the center of that tension sat the speed of light. Relativity demanded that it be absolute. Quantum mechanics demanded that everything fluctuate. If the universe was fundamentally uncertain, how could any speed be so rigidly fixed? For decades, this question lingered unanswered. The real reason nothing outruns light was not fully geometric. It was not merely about stretching clocks or contracting rulers. Those were symptoms, not causes. The deeper reason lay hidden in how quantum reality itself unfolds, in how particles move, not along single paths, but along every path at once. Uncovering that truth required a physicist who didn't just manipulate equations, but pictured how the universe actually behaves beneath them. Someone who trusted intuition as much as mathematics. Someone who replaced trajectories with histories. That physicist was Richard Feynman. And once he reframed motion as a sum over all possible paths, the speed of light stopped looking like a cosmic rule book and started looking like the only way reality can remain coherent at all. By the time Richard Feynman entered physics, the universe already appeared to run on well-tested rules. Yet, no one truly understood why those rules worked as flawlessly as they did. Einstein had shown how space and time bend and stretch to protect the speed of light, and his equations had survived every experimental test thrown at them. But relativity described spacetime as smooth and continuous, like a perfectly polished surface extending across the cosmos. Meanwhile, quantum mechanics, emerging at the same time, painted a very different picture. At the smallest scales, reality jittered, fluctuated, and refused to settle into certainty. Particles behaved like waves. Outcomes existed only as probabilities. Both theories were unquestionably correct. And yet, they spoke entirely different languages. The speed of light sat directly at the fault line between them. Relativity insisted that it was absolute and unbreakable. Quantum mechanics insisted that nothing was fixed until measured. Understanding why this one speed refused to yield required physicists to rethink something even more basic than motion itself. It required rethinking what a particle actually does between two moments in time. That rethinking came from Richard Feynman, a physicist who never trusted equations unless he could picture what they were saying. Where others saw abstract symbols, Feynman saw processes unfolding. Where others calculated, he imagined. He approached physics not as a list of rules, but as a story the universe was quietly telling. And one question obsessed him: what path does a particle take? Classical physics offered a comforting answer. A particle follows one definite trajectory, determined by forces acting upon it. Throw a ball, and it traces a single arc. Given the starting conditions, the path is fixed and inevitable. Quantum mechanics shattered that certainty. In the quantum world, particles are not tiny billiard balls carving clean lines through space. They behave like waves, spread out and uncertain, capable of interfering with themselves. A particle moving from point A to point B does not travel along one privileged route. According to Feynman, it travels along every possible route. Not metaphorically. Literally. Straight paths and curved paths, smooth trajectories and violent zigzags, paths that loop backward, wander outward, or detour through regions that seem completely absurd from a classical point of view. Even paths that stretch across the universe before arriving. All of them are included. At first, this sounds impossible, even nonsensical, until the quantum idea of superposition comes into focus. Before a particle is measured, it does not possess a single, well-defined history. Instead, it exists as a spread of possibilities, each one contributing something to what we eventually observe. Each possible path contributes a probability amplitude, a mathematical quantity that carries both size and phase. These amplitudes do not simply add the way ordinary numbers do. They interfere. Some reinforce one another, others cancel out. And this is where order emerges from chaos. Paths that wildly zigzag through spacetime accumulate rapidly changing phases. And when their contributions are summed, they cancel almost perfectly. Their influence disappears. Paths that stay close to the classical trajectory, however, accumulate similar phases. Their contributions align, reinforce one another, and survive. The classical path is not chosen because it is required. It emerges because it is stable. Classical motion, in this view, is not imposed by nature. It is what remains after all unstable possibilities eliminate themselves through interference. Hidden inside this accounting process lies the true explanation for the light speed limit. To see it, we need to look at how these amplitudes are calculated. Each path's contribution depends on a quantity called the diffraction, which measures how a particle moves through both space and time. For relativistic particles, the speed of light appears directly in this expression, linking distance and duration into a single spacetime structure. And here is where everything changes. When a path includes a segment where the particle moves faster than light, the mathematical character of the action shifts. Instead of producing a smoothly varying phase, it becomes imaginary. The phase of the amplitude begins to oscillate infinitely fast along that portion of the path. Infinitely fast oscillation means perfect cancellation. When all such paths are added together, every faster-than-light contribution cancels itself out with absolute precision. Not approximately. Not statistically. Exactly. These paths are not banned. They are not blocked by a cosmic rulebook. They exist in the mathematics, but they never survive the sum. They contribute nothing to reality. This is the quantum mechanical origin of the light speed limit. Einstein showed that reaching light speed requires infinite energy and infinite time dilation, making the barrier appear unreachable. Feynman showed why the barrier exists at all. The universe does not prevent faster-than-light motion. It refuses to assign it any physical meaning. Reality is constructed only from paths that can coexist without destroying one another. Faster-than-light paths cannot. This perspective transforms the speed of light from a rule into a consequence. It is not imposed on the universe from outside. It falls naturally out of the way quantum mechanics and relativity fit together. It also explains why apparent loopholes fail so consistently. Virtual particles in quantum field theory may appear to violate the limit inside calculations, but their unphysical behavior always cancels in the final result. Quantum tunneling may reshape wave packets in strange ways, but the information-carrying front never outruns causality. Quantum mechanics preserves the light speed limit automatically, not because physicists demand it, but because interference enforces it. Feynman's famous diagrams were developed as practical tools to calculate these sums over histories. Each diagram represents a class of paths, a possible story of how particles interact. Add all the allowed stories together, and the universe reveals what can actually happen. The diagrams look simple. The truth they encode is not. They show that nature does not select a single narrative for events. It considers every conceivable narrative, and keeps only those that remain self-consistent. Faster-than-light stories do not survive. They erase themselves. This is why the cosmic speed limit is so absolute. You cannot engineer around it, bypass it, or exploit it. Any attempt to do so collapses into incoherence, not because of engineering limits, but because beyond light speed, histories cannot assemble into reality at all. Once you see this, the question changes. It is no longer why we cannot move faster than light. It becomes why reality only allows stories that respect this speed. To answer that fully, we must now look at what happens as objects try to approach the limit. How energy, time, and geometry begin to diverge, and how infinity quietly enters the equations. That journey takes us into the physics of acceleration itself, and into the place where the barrier stops looking like a rule and starts looking unavoidable. Imagine for a moment that engineering has solved every practical problem. You're strapped into the cockpit of an impossible spacecraft, equipped with an engine that never runs out of fuel, never overheats, and converts energy into thrust with perfect efficiency. No friction, no losses, no limits except the ones written into reality itself. Your task is simple in description, if not in execution: accelerate until you break the light speed barrier. At first, everything behaves exactly as intuition expects. You ignite the engines, and the spacecraft surges forward. The velocity indicator begins to climb steadily, 1% of light speed, 5%, 10%. Each increase in thrust produces a corresponding increase in speed. Space offers no resistance. There is no air to push against, no medium to fight. Motion feels effortless. At 10% of light speed, you're already traveling at 300,000 kilometers per second. You could cross Earth's diameter in less than half a second. The moon would be only moments away. Yet, compared to your goal, you are still barely crawling. You continue to accelerate, 20%, 30, 40. The relationship between thrust and speed remains smooth and predictable. Everything feels normal. Classical intuition still works. The universe seems willing to let you go faster without complaint. Then, somewhere around halfway to the limit, something subtle begins to change. The engines are just as powerful as before. The thrust pressing you into your seat has not weakened. Fuel continues to pour into the reaction chamber at the same rate. And yet, the velocity increases begin to slow. Each additional burst of energy produces a slightly smaller gain in speed than the one before it. At first, the effect is easy to ignore. At 50% of light speed, the change is noticeable, but modest. At 70%, it becomes undeniable. By the time you reach 90%, the curve has steepened dramatically. The same engine that once produced large increases in velocity now struggles to add even a fraction of a percent. You are not fighting friction. You're not fighting drag. You're fighting spacetime. Einstein's equations describe exactly what is happening. As your velocity increases, your resistance to further acceleration increases as well. Early physicists described this effect by saying that your mass increases with speed. Modern physics uses a more precise language: your rest mass remains the same, but your momentum grows faster and faster as you approach the light speed limit. The mathematical factor governing this growth is called gamma. Gamma depends on your velocity relative to the speed of light, and it starts out harmlessly close to 1. At low speeds, it barely matters. But as velocity climbs, gamma grows slowly at first, then explosively. At 50% of light speed, gamma is about 1.15. Your resistance to acceleration is only 15% higher than at rest. At 90%, gamma rises to about 2.3. You now need more than twice the energy to achieve the same increase in speed you once did easily. At 99% of light speed, gamma exceeds 7. Every small gain now costs 7 times more energy than it would at low speed. At 99.9%, gamma climbs past 20. The universe is pushing back hard. Each additional digit of precision multiplies the difficulty. At 99.99%, gamma approaches 70. At 99.999%, it surpasses 200. The pattern is relentless and unforgiving. Each step closer to light speed demands exponentially more energy than the last. At exactly the speed of light, gamma becomes infinite. Not very large. Not impractically large. Infinite. The energy required to push any object with mass to light speed does not exceed some enormous but finite value. It exceeds all finite values. No amount of fuel, no technological breakthrough, no clever design can overcome mathematical infinity. The barrier is not technological. It is structural. This is not a thought experiment confined to equations. It plays out every day in real machines. Particle accelerators provide some of the most striking confirmations. In the world's most powerful accelerators, protons are pushed to speeds within a tiny fraction of light speed. By the time they reach these velocities, nearly all additional energy goes into increasing their momentum, not their speed. At facilities like the Large Hadron Collider, protons travel at more than 99.9999% of light speed. Adding more energy does not make them meaningfully faster. It makes them heavier in a relativistic sense. Harder to bend, harder to steer, harder to confine. This is why accelerator magnets must become enormously powerful. They're not compensating for friction or resistance. They are compensating for spacetime itself, becoming increasingly unwilling to allow further acceleration. Time dilation adds another layer to the barrier. As your spacecraft approaches light speed, time aboard begins to slow relative to the outside universe. At moderate speeds, the effect is subtle. Clocks tick only slightly slower. But as velocity climbs, the slowdown becomes dramatic. At 90% of light speed, time aboard your ship runs at less than half the rate of time back on Earth. A year for those you left behind becomes only a few months for you. At 99%, time slows to a crawl. For every year you experience, many years pass outside. As you approach the limit, time dilation grows without bound. At light speed, time stops entirely. This is not a poetic statement. It is a direct consequence of the equations. An object with mass cannot exist in a state where its own time does not pass. Reaching light speed would require freezing your internal clock completely, locking every atomic process in place. Such a state is not physically meaningful for massive objects. Length contraction completes the picture. As velocity increases, objects shrink along the direction of motion. Not because they are compressed by force, but because space itself contracts. At high speeds, this contraction becomes extreme. As you approach light speed, your length in the direction of travel collapses towards zero. At the limit, a massive object would be compressed into a geometry that cannot exist. An object with no extension along its direction of motion, yet still possessing internal structure. Time stops, length vanishes, energy diverges. These are not separate problems. They are the same problem seen from different angles. Together, they reveal a deeper truth. There is no continuous path that connects slower-than-light motion to light-speed motion for objects with mass. The equations do not describe a difficult crossing. They describe a missing bridge. The barrier exists because there is nothing beyond it for massive objects to occupy. Light itself behaves differently because it has no mass. Photons do not slow time as they accelerate. They do not contract as they approach the limit. They are born at light speed and exist only there. For them, emission and absorption are not separated by duration. Everything else is excluded. And so the universe reveals the barrier not as a wall but as an asymptote, a line you can approach forever yet never reach. No matter how powerful your engine or how patient your journey, the closer you come, the more reality resists. Not through force, but through geometry, through time, and through the very definition of energy and motion. Approaching light speed does not merely become harder. It becomes impossible in principle. And yet, even this does not fully explain why the barrier exists. It explains how energy, time, and space conspire to protect it, but not why reality is structured this way in the first place. To answer that, we must now confront what happens if the barrier were crossed, what faster-than-light motion would mean for causality itself. That realization takes us beyond engines and equations and straight into paradox. Up to this point, the speed of light has looked like a physical barrier, a limit enforced by energy, time dilation, and geometry. But the deeper danger of crossing it has nothing to do with engines or fuel. It has to do with cause and effect. To see why, we need to step away from rockets and particles and instead look at how events relate to one another across space and time. In Einstein's universe, space and time are woven together into spacetime, and not all events are connected in the same way. Some events can influence one another. Others cannot. This distinction is not a matter of technology or distance. It is a matter of geometry. If one event can influence another, every observer in the universe agrees on their order, cause always precedes effect. The sequence is absolute. But if two events are separated by too much space and too little time, farther apart than light could travel between them, something strange happens. Those events become space-like separated. They cannot affect each other in any way. And because there is no causal connection, different observers moving at different speeds can disagree about which event happened first. One observer might see event A occur before event B. Another might see B before A. A third might see them as simultaneous. This disagreement is not an illusion. It is built into spacetime itself. Normally, this causes no problems, because space-like separated events are causally disconnected. Nothing travels between them. No influence flows. No contradiction arises. But the moment faster-than-light motion enters the picture, everything breaks. If you could travel faster than light, you could move between space-like separated events. And by doing so, you would turn events with no fixed temporal order into events with a causal connection. That is where paradox begins. Imagine sending a signal faster than light. In your frame of reference, the message travels forward in time. But because different observers disagree on the ordering of space-like events, there will always exist another frame of reference in which that same signal arrives before it was sent. This is not speculation. It falls directly out of Einstein's equations. Faster-than-light motion is mathematically equivalent to backward time travel for some observers. And once information can travel backward in time, causality collapses. You could receive a warning about a decision you haven't made yet, and then choose differently, preventing the warning from ever being sent. You could observe the effects of actions whose causes lie in the future. You could build closed causal loops where information creates itself with no origin at all. These are not philosophical puzzles open to interpretation. They are logical contradictions. A universe that allows faster-than-light communication cannot define consistent cause and effect. The mathematical structure of spacetime stops making sense. Physics loses the ability to predict anything reliably, because the future can rewrite the past. This is why the light speed limit is not just about motion. It is about protecting causality itself. Physicists explored this danger deeply in the 20th century, searching for loopholes that might allow faster-than-light motion without destroying logic. Over and over, the same wall appeared. One proposed loophole involved hypothetical particles called tachyons. Tachyons were imagined as particles that always move faster than light, just as ordinary particles always move slower. They would never slow down to light speed, just as electrons can never speed up to it. On paper, the idea seemed symmetrical and elegant. But tachyons came with a fatal flaw. In some reference frames, a tachyon would move forward in time. In others, it would move backward. Its energy could become negative. Signals carried by tachyons could arrive before they were sent. The mathematics allowed tachyons to exist only at the cost of causality. No experiment has ever detected such particles. No consistent theory has ever successfully incorporated them without generating paradoxes. Tachyons remain mathematical curiosities. Warnings more than possibilities. Another apparent loophole comes from quantum mechanics itself. Quantum tunneling sometimes appears to allow particles to cross barriers faster than light. In certain experiments, the peak of a wave packet seems to emerge on the far side of a barrier sooner than light could have crossed the same distance. At first glance, this looks like a violation. But the illusion dissolves under careful analysis. Information is not carried by the peak of a wave packet. It is carried by its leading edge, the first disturbance that could possibly encode a message. That leading edge never outruns light. What tunneling does is reshape the wave packet, not transmit information superluminally. Every careful experiment confirms this. Quantum mechanics respects causality with ruthless consistency. Even more ambitious ideas have tried to bypass the limit by manipulating spacetime itself, rather than moving through it. In 1994, physicist Miguel Alcubierre proposed a solution within general relativity that captured the imagination of science fiction writers and physicists alike. The Alcubierre warp drive would not move a spacecraft faster than light locally. Instead, it would contract spacetime in front of the ship and expand it behind, allowing the ship to ride a moving bubble of spacetime itself. In principle, the ship would never exceed light speed within its local environment. On paper, the equations allowed it. Reality did not. Creating such a spacetime distortion would require enormous quantities of exotic matter with negative energy density. Matter that repels gravity rather than attracting it. While quantum mechanics allows tiny, fleeting amounts of negative energy, the quantities required for a warp bubble exceed the total energy content of the observable universe. Even worse, later analyses revealed additional fatal problems. The front edge of the warp bubble would accumulate radiation and particles to catastrophic levels. When the bubble collapsed, that energy would be released in a burst powerful enough to sterilize entire star systems. Worse still, occupants inside the bubble could not control or shut it down, because signals from inside cannot reach the bubble's boundary faster than light. The drive is mathematically interesting. It is physically impossible. Wormholes offer another seductive escape. If spacetime could form tunnels connecting distant regions, one might step through and emerge light years away without ever traveling faster than light through the tunnel itself. General relativity permits such solutions under certain conditions. But once again, stability demands exotic matter with negative energy density. Without it, wormholes collapse instantly. With it, they destabilize causality. A traversable wormhole can always be turned into a time machine, producing the same paradoxes as faster-than-light travel. Nature appears to reject these possibilities at a fundamental level. Every road that leads past light speed leads straight into causal contradiction, and the universe does not tolerate contradiction. This brings us to one of the most misunderstood phenomena in modern physics: quantum entanglement. Entangled particles display correlations that appear instantaneous, regardless of distance. Measure one particle's state, and the other state is immediately determined, even if it lies on the other side of the galaxy. Einstein famously called this spooky action at a distance. But entanglement does not transmit information. When you measure one particle, the outcome is random. You cannot choose the result. The distant observer also sees randomness. Only when the two of you later compare results, using ordinary light-speed limited communication, do the correlations become apparent. No message outruns light. Quantum mechanics flirts with non-locality, but it stops precisely where causality would be violated. This is not accidental. It is enforced by the mathematical structure of the theory itself. Physicists call this the no-communication theorem. Entanglement creates correlations, not control. Knowledge still travels at light speed or slower. This pattern repeats everywhere. Every apparent loophole collapses under scrutiny. Every attempt to bypass the cosmic speed limit either fails experimentally, demands impossible conditions, or destroys causality outright. This is not because physicists lack imagination. It is because causality is more fundamental than motion. Cause must precede effect for the universe to be intelligible at all. Memory must record the past, not the future. Information must have an origin. Choices must not erase themselves. The speed of light enforces this structure. It defines the boundary between what can influence what. It carves spacetime into regions of possible connection and permanent separation. Inside your future light cone lie all the events you could ever affect. Outside it lie events forever beyond your reach, no matter what you do. This is not a technological limitation. It is a logical one. Faster-than-light travel would not merely allow us to go farther or faster. It would destroy the distinction between before and after. And once that distinction collapses, physics collapses with it. The universe seems to understand this at a deep level. It does not merely make faster-than-light travel difficult. It makes it meaningless. The equations do not describe a forbidden region beyond the barrier. They describe a breakdown of coherence itself. To cross the light speed limit is not to enter a new domain. It is to exit the domain where reality can be consistently defined. And yet, there is still one question left unanswered. Why does the universe care so deeply about causality? Why is this structure baked so thoroughly into spacetime, quantum mechanics, and every known interaction? To answer that, we need to look at the largest scales of all, at horizons, black holes, and the ultimate reach of cause and effect across the cosmos. That takes us into the final shocking truth of this story. When physicists say that nothing can travel faster than light, it's easy to hear that as a limitation, a frustrating ceiling imposed on motion, exploration, and ambition. But at the largest scales of all, the speed of light reveals itself as something far more profound. It is not a restriction placed on the universe from the outside. It is the structure that determines what the universe can even be. Every event in spacetime occupies a precise geometric position, and from that position unfolds a shape that defines all possible connections. Physicists call it a light cone. The past light cone contains every event that could possibly have influenced the present moment. The future light cone contains every event that this moment could ever influence. Everything outside those cones is permanently disconnected, unreachable, unobservable, and causally irrelevant. The speed of light defines the slope of those cones. It decides which events can be causes, which can be effects, and which are forever strangers to one another. This geometry is not abstract mathematics. It is the architecture of reality itself. Nowhere does this become more dramatic than near a black hole. When a massive star collapses under its own gravity, space-time curves inward so steeply that a boundary forms, the event horizon. At that surface, the escape velocity equals the speed of light. Light emitted inward does not slow down or weaken. It continues to move at its usual speed. But space-time itself is falling inward faster than light can climb outward. Beyond the horizon, escape is no longer a spatial question. It becomes a temporal impossibility. Inside a black hole, the singularity lies in the future of every possible path. No matter which direction you move, you're moving toward it. Just as moving forward in time always carries you into tomorrow. Escaping the black hole would require moving backward in time, something the universe does not permit. The speed of light enforces this one-way structure. A black hole is not a wall or a prism. It is a causal boundary carved into spacetime by the same limit that governs every interaction everywhere else. The same speed that prevents faster-than-light communication also seals regions of spacetime away forever. This same principle defines the limits of the observable universe. The universe is about 13.8 billion years old. Yet the observable horizon lies roughly 46 billion light-years away. That apparent contradiction exists because space itself has been expanding while light traveled through it. Light that left distant regions billions of years ago crossed a universe that was stretching as it moved. By the time it reaches us, the source has been carried much farther away. Beyond that horizon lie regions we will never observe. Not because light is too slow, but because causality itself cannot bridge the gap. Those galaxies are not merely far away in space. They are separated from us in time and causality. Nothing that happens there can ever affect us. Nothing we do can ever affect them. They lie outside our future light cone, permanently inaccessible. As cosmic expansion accelerates, this isolation deepens. Distant galaxies are already slipping beyond causal reach. In the far future, only the galaxies gravitationally bound to our local group will remain visible. Everything else will fade from view, erased not by darkness, but by the geometry of spacetime itself. The speed of light creates this cosmic loneliness. And yet, without it, the universe would be unrecognizable. A finite speed of causality is what allows structure to form at all. If information propagated instantaneously, every region of the universe would immediately equilibrate with every other. Temperature differences would vanish. Stars would struggle to burn steadily. Complex chemistry would dissolve before it stabilize. The universe needs delays. It needs time for cause to precede effect. It needs information to spread gradually, not instantly. The speed of light sets that pace. At a deeper level, it also shapes the arrow of time itself. Most fundamental equations of physics are time-symmetric. Run them forward or backward, and they still work. And yet, time clearly flows in one direction in our experience. We remember the past. We do not remember the future. Entropy increases. Disorder spreads. This arrow of time is tied to information. Low entropy states contain information packed into small regions. As time passes, interactions spread that information outward, creating correlations with the surrounding environment. That spreading cannot happen faster than light. The finite speed of causality determines how quickly entropy increases across space and time. Memory works because causes come before effects. Thought works because signals travel in sequence through neural networks. Consciousness itself depends on a universe where information cannot arrive before it is created. The speed of light protects this structure at every scale, from subatomic interactions, to the firing of neurons, to the evolution of galaxies. This is why physicists often say that the speed of light is badly named. It is not really the speed of light. It is the speed of causality. The conversion factor between space and time. The tempo at which reality updates itself. In the geometry of spacetime, distance and duration are not separate quantities. They are different ways of measuring the same underlying fabric. The speed of light is the number that translates between them. 1 second of time is equivalent to roughly 300,000 kilometers of space. This is not a statement about motion. It is a statement about geometry. This is why physicists often simplify their equations by setting the speed of light equal to 1. Doing so strips away the illusion that space and time are fundamentally different. It reveals that moving through space and moving through time are aspects of the same process. This same conversion factor appears in Einstein's most famous equation, E equals mc squared. Mass and energy are not merely related. They are identical quantities measured in different units. The speed of light squared is the conversion rate. Multiply a small mass by this enormous factor, and you reveal the tremendous energy bound inside matter. Einstein showed how this geometry shapes motion, energy, and gravity. He revealed how spacetime bends and stretches to preserve causality. But Einstein did not explain why the universe insists on this structure so absolutely. That insight came from quantum mechanics. Richard Feynman showed that the light speed limit is not enforced like a law. It emerges from how reality is built. In the quantum view, particles explore every possible history, but only certain histories survive interference. Paths that violate causality cancel themselves out before they can contribute to anything real. Faster-than-light histories are not forbidden. They are meaningless. They cannot assemble into a coherent universe. This is the deepest reason the limit cannot be broken. There is no faster-than-light realm waiting beyond the barrier. There is no hidden shortcut or deeper layer where causality relaxes its grip. The mathematics simply does not construct reality from those possibilities. Asking how to go faster than light is like asking how to arrive before you leave. The question assumes a structure that does not exist. And once you see that, the speed of light stops feeling like a wall. It starts feeling like a foundation. It is the reason stars burn slowly enough for planets to form. The reason galaxies evolve instead of instantly collapsing into equilibrium. The reason the past stays fixed while the future remains open. The reason cause can produce effect without contradiction. The universe does not prohibit faster-than-light motion. It cannot define a reality in which such motion exists. This is the deepest secret Feynman helped uncover. Not a new rule, not a deeper barrier, but a realization that consistency itself is what governs existence. Only certain tempos allow histories to add together instead of canceling themselves out. Only certain speeds allow cause and effect to remain meaningful. The speed of light is that tempo. It is the frame rate of the cosmos. Every particle, every force, every interaction unfolds to this rhythm. The universe cannot accelerate its beat, because the beat is not separate from the universe. It is the universe. The past light cone contains everything that could have shaped you. The future light cone contains everything you could ever influence. Beyond both lies the vast majority of spacetime, real, immense, and forever unreachable. This is not a tragedy. It is the price of coherence. Without this limit, reality would collapse into paradox. With it, the universe can tell a consistent story, one that unfolds from cause to effect, from past to future, from simplicity to complexity. The speed of light is not the fastest thing in existence. It is the reason existence can happen at all. And once you truly understand that, the limit no longer feels like something holding us back. It feels like the ground beneath everything we are. There are over 365 million people subscribed to this channel. Thank you.